All right, so in this video, I wanted to go over the how to plot stuff using Google Sheets and go through the first two examples. So data set one, we got time and position. Now, whenever you're plotting anything in Google Sheets, you want to make sure that whatever you want to be on the x-axis or horizontal axis is the first column, then whatever you want to be on the vertical axis is the second column. We can And then also everything that you want to be here has to just be numbers. You can't have any letters, spaces, whatever. It won't recognize it as numeric data. It'll think it's something else. So that's why like time and position, you put what it is measured in your units in the column header, but not down below. So let me highlight these. I'll do insert, chart, and it makes a position versus time graph. All right, whoops, I forgot. The first one is non-linear. So actually, let's skip to data set two. So distance versus force, highlight these, insert, chart. That one's already linear. I'm going to move that over, make it a little bit smaller. There we go. All right, it's a scatter chart, which is what we want. We don't do a line chart. We don't play connect the dots. We do a scatter and instead do a best fit line. Now, one thing, first off, you have force versus distance, and it'll already be in the correct unit, or the correct title, the vertical axis or dependent variable versus the horizontal axis or independent variable. And everything will be labeled if you set this up properly beforehand. So make sure you have your columns right, and it'll make things easier on your graph. But anyway, let's go to Customize, Series, Trend Line, and we can see it is linear. And under label, use equation. All right. So this gives us, it says in the legend here, it says the line represents negative 0.395 times x plus negative 8.33 e negative 0.4. That's negative 8.33 times 10 to the negative fourth power. So that's the equation of that line of best fit. It's saying the line of best fit is given by 0.395 or 0.395 x minus 8.83 times 10 to the negative fourth power. So in other words, that's our x-intercept. That's our slope, and x, well, that's the variable. But if we look at what's actually on our y-axis, it's force. And our x-axis is actually distance. So you've got force equals 0.395 times distance. Oh, negative. Missed that negative sign. Negative 0.395 times distance. And this is so small compared to everything. Imagine shifting this decimal place 4 times. I'm going to assume that that's about equal to 0. Now we just need, so down here where it says equation, we would say F equals negative 0.395 times D. Now, we do need, though, units in this. So what are the units of the slope? Well, we have rise over run, newtons over meters. So really, we want to say F equals negative 0.395 newtons per meter times D. So then when you would multiply that by the units of whatever distance, the meters, you'd have newtons per meter times meters. You get newtons back. All right, so that's already linear. Now let's go back to data set one. This is not linear, it's curved. I don't know what kind of curve it is, but here I'll click on these three dots, go to edit chart, customize, series, trend line. I can do type polynomial. That doesn't tell the whole story, like necessarily. Now, in this case, yeah, it turns out the data is quadratic. We'll get to that in a sec. I'll show the equation. But I can also do a cubic and get a really good fit. I can do a quartic and get a really good fit. In fact, there's 1, 2, 3, 4, 5, 6, 7, 8 data points. So 2 points perfectly define a line, 3 points perfectly define a parabola, 4 points perfectly define a cubic, and so on. So I could do a seventh order polynomial and get a perfect, exact, no error whatsoever fit. But just because I can do that with the math doesn't mean that's what's actually going on. So what I like to do with things like this, when I see it curves, goes through zero, instead of a polynomial, I like to do what's called a power series fit. So this is telling me that the curve of this is 3.1 times x to the 1.98 power. Now, it's highly unlikely physically that it's actually the 1.98 power. No measured data is going to be perfect. It's far more likely that that's the second power. That, in other words, y is equal to 3.1 x squared. So this is a quadratic relationship. Now, to linearize this, all right, and let's get the actual variables. Our equation may be this, but remember, position, our horizontal axis is position, or sorry, vertical axis is position, and our horizontal axis is time. So we have x equals 3.1 t squared. Now, the thing with these curve fits, especially, the slightest things can throw them off. This data is pretty good, but if you have larger errors, it might give you weird exponents, weird coefficients out front that throw you off from what's really going on. But knowing that this should be quadratic, here's what we're going to do. So we have x is equal to, doesn't even have to be 3.1. Let's do this in general. X is equal to some constant times t squared plus plus the initial velocity times t, or plus some other constant times t, but that's zero, plus x naught. If we compare that to a line, y equals m times x plus b, here we have a constant being added on. We can match those up. Now in this case, the intercept is 0, 0, so we don't have to worry about that either. In fact, this doesn't work if we have a linear term. we can put position, keep that our y-axis as position. But here, we're going to want to stretch out the x-axis or horizontal axis. If we could make this a line, if this point were further to the right, if this point were further to the right, if that point were further to the right, if that point were further to the right, we can do that by squaring our x-axis. In other words, instead of plotting position versus time, let's let our x-axis be time squared. And we can see it lines up when we compare the equation we think we have, x equals some constant times time to the second power, to the equation for a line, y equals m times x. So our position's not changing. I can just copy this over. I can do Control C, Control V. And for the time, I want to do time to the second power. I also have to make sure I update my units. So parentheses s squared. Now I could go through and all these numbers are really easy, but for repeated calculations, let's let Google Sheets do it for you. So here's what I do. Equal sign. That tells it I want to calculate something. I want it to take whatever's in this cell and square it. So shift 6 or caret 2. Now, the reason why I might want to do that, let's say I have to go back and change my data. Let's say that this was 20. Well, you can see it calculates that as 400. Let's say that this was 10. It'll automatically update that to 100, and so on. And then, okay, so take that. I want it to be whatever's in that cell squared, so caret 2. But there's an even better way. What I could do here, when I click that cell, move my mouse to the bottom right, it'll turn into a black plus sign, click and hold, and then drag it down. And it'll repeat those formulas for all the cells that you drag it down to. So this is that cell squared. This is, you can see B5 squared, so it's that cell squared. This is B6 squared, so it's whatever's in this cell squared, and so on and so forth, up to this is B10, so whatever's in this cell squared. You can see that up here. So now that we have that, let's plot it. Insert chart, and we can see that that graph is linear. Make sure that there's some spacing between your, at least one column of spacing between your new tables that you're going to plot with and any previous tables. Otherwise, sometimes it can cause plotting errors and it doesn't know that you're trying to do a y versus x scatter plot. All right, so we got that over there. Edit chart, customize, series, trend line, label, use equation. So it's 2.99x plus 0.0281. Just like the last one, or let's see. So Google Sheets gives us the equation. Y equals 2.99x minus 0.0281. But we got to remember, just because these are the variables it gives us, that doesn't mean that's what's actually going on. Once again, our y-axis is actually position. So X R equals 2.99. I'm going to leave room for units. Our x-axis is actually time squared. Minus 0.0281. Let's figure out units. So this is the y-intercept. The y-axis has units of meters. And slope is rise over run. So we have meters divided by second squared, or meters per second squared. So that's the equation that we actually get translated into the appropriate variables. So the position is equal to 2.99 meters per second squared times time squared minus 0.0281 meters. But this is so small that I think we can again, compared to what we have, neglect that as 0. And just drop that. All right, so there we go. That's the equation for data set 1, and that's how we linearized it. You look at the type of relationship you get. In this case, it was quadratic, so y was proportional to x squared, or position was proportional to time squared, rather. So I plotted position versus time squared. And that's all there is to it. Now, not all of them will be square, but look at the relationship, especially the power fit is really handy here. Look at the kind of relationship it gives you. All right, so that's how you do plotting in Google Sheets and how you do linearization.